it later. So hello everybody. My name is Khaled Hamsho. I've given a few PAL sessions before. And yeah, we're gonna do reactive oxygen species and antioxidants. So yeah, let's get started. Let's see. So again, let's just quickly try to get through this lecture in maybe like a few minutes. Like 30 minutes to an hour. Hopefully it won't take too long. If you have any questions, you can stop me at any time. You can just type in the chat. I'm keeping an eye on that all the time. I don't mind repeating a point like 10 million times. So if you are confused about something, just type it away or maybe open up your mic, whatever you're comfortable with. So let's get started. So these are the learning objectives of the lecture. Let's get those. So first off, before we start learning about the reactive oxygen species and the antioxidants, let's start with identifying what's going on. So first off, some terminology to be said, so you're more oriented towards the lecture. First off, oxidation and reduction. So oxidation and reduction, all you need to know, you've taken this in high school before, I hope. And all you need to know about this or trying to remember is that oxidation is the loss of electrons. So for example, you have a molecule, it lost its electrons, that's called oxidation. Reduction is a gain of electrons. So when we say a molecule is reduced, that means it has gained an electron. So let's just take an example down here very quickly. Did someone say something? Okay. So let's take an example down here real quick. So if we have, say, this molecule over here, this electron over here in this molecule, if this electron moves from this molecule to this molecule is set to be oxidized because it lost this electron right here. Now, because this electron went to this molecule, this is called reduction. So this molecule got reduced. So it gained an electron. So honestly, that's it for that. Now this brings me to free radicals. So what is a free radical? A free radical is a molecule containing one or more unpaired electrons. I'll show you an example in just a second. So these unpaired electrons, chemically reactive, highly unstable. Now we have different types of free radicals. They could be peroxide, hydroxyl radical, hydroxyperoxide, lipid peroxide radical, etc., etc. These are all different types of free radicals. Just be aware of them. You don't have to memorize them per se, but just have an idea of what they are. So like if you see their names, you just can at least recognize them. Now, what are reactive oxygen species? Now, reactive oxygen species is basically a broad term that encompasses both free radicals and non-free radicals. Now, the thing is, non-free radicals are still reactive. They still react with other things. They're still reactive. But the only difference, they're not considered free radicals. The reason is because they don't have a free electron. You remember what the definition of a free radical is? It's unpaired electrons. Now, this is the only difference, but for all purposes, reactive oxygen species is the term we'll be mostly using because it is the reactive thing. They're still both harmful. They're still both equally as bad. So this is what we'll be focusing on. And yeah, that's it for free radicals. So I just want to show the concept over here. So let's suppose this molecule right here, the one that's angry over here, is the hydroxyl free radical. Now, what happens is in these free radicals, the reason they're harmful is because they are unstable molecules. Because they are very highly reactive, they tend to react with molecules that are very stable. For example, lipid molecules or phospholipids, the things that compose the membrane. So when they react with this, they steal this electron. So they take it over here. Now, once they steal it, this becomes unstable. Once this becomes unstable, this becomes unstable. Once this guy becomes unstable, it steals another electron from another guy. And a chain reaction just starts. Like this free radical generates this free radical, generates another free radical, and it starts a whole cascade. And the thing is, this cascade is very harmful. The reaction that occurs between these two is destructive. That means it destroys proteins, it destroys DNA, it destroys lipids, it destroys carbohydrates, it destroys all sorts of molecules. That's why we don't want this reaction to happen. And that's why we have something known as an antioxidant right here. This antioxidant, what it does is that it provides this electron. So you know how this guy is missing an electron right here? It donates this electron to make it stable. So it makes the molecule stable without this molecule having to steal from somewhere else. So this guy would still be stable, even though he gave away an electron, because it's considered to be an antioxidant. But it also stabilized this molecule right here, which prevents the damage. Now, this is generally the entire lecture. This is the whole lecture. This is what the lecture boils down to, these three concepts. So is that clear? By the way, do you guys hear me? Any questions here? Because if you understand this, then the whole lecture will be super easy, very quick. Awesome. All right. So I'll move on. If anyone has a question, you can just stop me. Could you repeat? Sure, I'll repeat it. So very quickly, so a free radical is a molecule that's missing an electron. It tries to steal electrons from stable molecules. When it steals the electron, say this guy goes over here, this becomes unstable. So this guy becomes unstable. Once this guy is unstable, it starts attacking other molecules and stealing their electrons. It doesn't fight this guy back, usually. It steals from other molecules and makes them unstable. Now, the reason this is harmful is because this reaction destroys proteins. It destroys proteins, it destroys DNA, it destroys many different components of the cells. And that eventually, this all eventually leads to cell, oh dear, my bad. This all eventually leads to cell death. And that's why this is harmful. Now, antioxidants, what they do is they take their electron, they donate it right away. It's like they see a free radical form, they quickly donate this electron in order to cover or stabilize this free radical. And when they donate this electron, they don't become unstable. They remain stable. They remain stable. And they stop this cascade from occurring. So this is the concept of free radicals. Is that clear? Well, anyways, we'll be repeating a lot. This lecture is going to repeat a lot. So if you don't get it now, hopefully you'll get it later. So yeah. Next, what do free radicals, like what are their properties? What do they do? So number one, they're highly reactive. We saw the reason they're highly reactive is because they're missing an electron. There's no electron, so they try to steal electrons. They try to steal them. And when they steal these electrons, that's called a reaction. When they steal electrons, that's called a reaction. And when they react with other molecules, they make them unstable. And that basically leads to the instability of the molecule and eventually the breakdown of the function. Second, free radicals have a very short half-life. You don't need to know the definition of a half-life, I think, but all you need to know is that they don't last for too long. So most of them last seconds. Someone want to say anything? So most free radicals last for a few seconds because they quickly react. The reason they're short-lived is because they react quickly and they stabilize, but that causes destruction to the other molecules. Now, we said it causes destruction to other molecules. This means that it generates new radicals. So basically when, say, OH-, the hydroxyl free radical, this guy over here, this guy, if it reacts with, say, a protein, once it reacts to the protein, this protein becomes a free radical. This guy becomes a free radical. And this guy starts to attack other proteins. And they all start attacking each other. And that's why it starts a chain reaction. What do we call it? And finally, they cause damage to these molecules. So we said, as they react, they damage the molecules, the cells, and the tissues in the body. Now, just a small point, this is pure memorization, but most free radicals are derivatives of oxygen. That means they have an oxygen molecule inside of them, but some of them are derivatives of nitrogen. These are mostly have to do with like immune system. And yeah, that's mostly it there. But most free radicals are oxygen. They involve oxygen. Yeah, that's about all here. So again, this is a list of the free radicals right here. These are reactive oxygen and nitrogenous species. These are these are both reactive oxygen species and nitrogenous species. They're all free radicals. Well, they're not all of them are free radicals. My bad, that was a misnomer. They're all reactive. That means they cause damage to the cell. All right. So because we have a bunch over here, let's discuss them. So the most important ones to know is this guy right here, hydroxyl peroxide, hydrogen peroxide, nitric oxide, and that's it really. That's genuinely, these are the most known ones in the body. So I would memorize these, or at least just recognize them. The rest are cool to know. Like, they're cool, sure, but they're not very relevant, at least not very significantly. So these are like in pesticides and other things. So generally, these are the four most important free radicals to focus on. I think I highlighted them here. So superoxide, singlet oxygen, hydroxyl free radical, hydrogen peroxide. And their half-lives, you don't need to remember this, I think, but just remember they're all short-lived, minutes, microseconds. Even hydroxyl free radical is in nanoseconds. All this means, by the way, this half-life thing, all it means is that the longer the half-life, the shorter the half-life, as the half-life decreases, it means that the molecule is more reactive. It's more reactive. It's quickly reacting with other molecules. So it's disappearing very quickly. And that means it's more dangerous. So the hydroxyl free radical is one of the most powerful free radicals in the, in the body that gets generated. And it's very bad. That's why it only lasts for a few seconds. Is everything clear so far? If I'm going too fast, just let me know, guys. You can stop me at any point. All right, next. Anything in the chat? All right, cool. All right, so we talked about the hydroxyl free radical. We said it's very important. Now, how does it form? Usually, what happens is, like, there's a Fentone reaction. Just remember the name of it. You don't need to know the exact specifics here. You don't need to write it to like memorize any of this. All you need to know here is that it's called the Fentone reaction, and the Fentone reaction involves iron. What do we call it? Just remember the Fentone and Fe right here. You can remember that. So it involves iron. What happens is this hydrogen peroxide, we said it's not a free radical, but it can generate the hydroxyl free radical. If hydrogen peroxide stays in the body for too long without being cleared by the defense mechanisms, which we'll discuss in a bit, it'll eventually turn into the hydroxyl free radical, like all of these. And all this does is it damages the body very significantly. One more thing is that any metal, like iron, zinc, or any transitional metal you can think of, is usually a very reactive. That means it reacts a lot in the body. Now, the reason it's not very significant is because they have transporters. They're transported in the body. So they're already bound and reacted to something that's transporting them around. But if they were in their free form, they would act just like free radicals. Yeah, is that clear? Basically, all you need to know, Fentone reaction with iron, hydrogen peroxide makes the hydroxyl free radical. And other reducing agents can make this. You can just memorize these points right here if you want to, but it's sort of irrelevant right here. But these guys can make the ferrous iron. But just remember that the reactions are through the transition metals. So in order to form the hydroxyl free radical, you need hydrogen peroxide and iron. That's all you need to focus on. A very important slide over here. All right, so this is where we get to more important things. So the pathways of free radical formation. So we've been talking about free radicals for a while now, but how do they form? Like, how do they occur in the body? Well, first off, we have a couple of examples, and we'll go over them again in a bit. There's a couple of slides that do cover this stuff. So let's try to understand what's going on here. So there's a bunch of enzymes in the body, and there's a bunch of reactions in the body that by just pure chance, they generate free radicals or reactive oxygen species. One of them is through an enzyme called xanthine oxidase. This thing is responsible for nucleotide synthesis. it's not important to know that, but it's just to orient you. This enzyme, by accident, can generate the superoxide free radical. And this and other processes as well can generate it. For example, in the mitochondria. The mitochondria, it says mainly in complex 1 of the electron transport chain. Remember aerobic respiration? My bad. Remember aerobic respiration from like the glycolysis TCA cycle, etc. All of that. Some of the oxygen there can be converted into superoxide, which is reactive. Now, there are other enzymes and many examples. For example, NADPH oxidase that can also generate this free radical right here. Let's focus on the main concept over here. So once we generate this guy is mostly, I want you to remember this guy for mostly superoxide. This guy right here, if you can't see clearly, this guy. The reason this guy is important is because this is mostly the free radical that gets generated most of the time. So this free radical through an enzyme, this is a defense enzyme inside the body. It's known as superoxide dismutase, or SOD for short. This converts this into hydrogen peroxide. And you're like, wait a minute. So it converted a free radical to a reactive oxygen species, like another free radical? And you're like, well, yeah, but like your body can't deal with this right away. So it's got to convert it to this guy first, and then it converts it to water. This is how you deal with a superoxide free radical. Now, how it turns it into water is done through another enzyme known as catalase. Catalase converts hydrogen peroxide into water. And obviously, water is not toxic. So yeah, it's good. Now, how it does it is through another enzyme or another molecule right here. It's known as glutathione, reduced glutathione. The reason it's reduced, we mentioned at the beginning, reduced means it has an electron. It gained an electron. It gained it from the previous reaction down here. Now, this electron gets donated to this hydrogen peroxide, and it turns it into water. Now, this donation occurs through another enzyme known as GSH peroxidase. This is just pure memorization. It converts this into this. Now, once it donates this electron, it becomes oxidized because it lost an electron. So it becomes this, glutathione, but oxidized. Now, this guy can gain an electron. How does it gain it again? There's another enzyme. It's called GSH reductase. Remember, it's called reductase. That means it reduces. So it'll reduce this into this. How it does it? It takes an electron from NADPH. Now, if you remember this molecule, this came from the pentose phosphate pathway. If you remember, it was one of the molecules that were generated from the pentose phosphate pathway. This is very important because it donates the electron to GSH and reduces it again. So it can fight the hydroxyl free radical right here. Yeah, that's about all here. Is everything clear so far? I can repeat. All right. Just to quickly read the line over here, glutathione is a major reductant. So reductant meaning antioxidant here. I think I elaborated on it right here. Yeah, chat. Can you please repeat? Sure. I'll repeat this very quickly. I'll just focus on this side right here. So first off, let's start from the beginning over here. So for whatever reason, let's skip all this right now. We'll come back to it in just a minute. For whatever reason, we generate this free radical right here. This free radical is known as superoxide. Superoxide. Now, we need to deal with this very quickly. We said free radicals are bad. We don't want them around. So the body, through its defense mechanism, tries to deal with this superoxide. How does it deal with it? First off, there's an enzyme found inside the body. This is known as superoxide dismutase. Superoxide dismutase converts superoxide into the hydrogen peroxide. So it converts it into hydrogen peroxide. Now, you're like, wait a minute. Hydrogen peroxide is still bad for you. And I'm like, yeah, totally agree with you there, sir. But the problem with hydrogen peroxide, or the problem with superoxide, my bad, this guy over here, it can't be dealt with right away. It needs to be converted into another one before you deal with it. So you convert it to hydrogen peroxide. Now, what do? Now, you want to convert this hydrogen peroxide into water. You want to turn it into water. How do you turn it with water? You turn it to water through the enzyme known as catalase. Well, how does catalase convert it into water? It needs an electron. Where does this electron come from? It comes from glutathione. If you know, GSH over here stands for glutathione, but in reduced form. What do we remember about reduced? Reduced means it has an electron, so it's carrying an electron. This electron gets donated into hydrogen peroxide. Once this electron is donated to hydrogen peroxide, through the help of GSH peroxidase, so these two enzymes work together, through the help of this enzyme, it converts hydrogen peroxide into water. Water is not toxic, it's not a free radical, it's good. What happens here is this has lost an electron. It no longer has the electron. It's now called oxidized glutathione. Oxidized glutathione needs to be regenerated because it needs to quickly be in reduced form in order to protect the body from, what do we call it? To protect the body from free radicals. So how does it do it? It needs an electron from somewhere else. This is an electron right here. You see this hydrogen atom right here? This is an electron. I don't know why, but it's just considered an electron. We're not here to discuss why is it an electron, why is it not. So this electron gets donated to this guy right here. You see the oxidized glutathione. Through the help of an enzyme known as glutathione reductase, or GSH reductase, it converts it from GSSG, which is the oxidized form, into the reduced form, which is GSH. And now this guy is ready again to deal with another hydrogen peroxide. Now imagine this, you have millions of these inside your body. You have millions of catalases inside your body, millions of superoxide dismutase, millions of these. So they're constantly regenerating. So this is the entire cascade for this protection system inside your body. This is your antioxidant defense mechanism. This is the antioxidant defense mechanism. All right. Do you guys want me to repeat again? Any specific points you don't get? I can repeat specific points if you're lost. We'll get into these right here on the side later. Everything clear? All right, great. All right, so let's move on to the next point here. So we said reactive oxygen species and whatever, like where do they come from? Like we said, we know how to deal with them. We know they're bad. Like where do they come from? Well, they come from many different things. Now, obviously, you don't need to memorize all these, but these are just examples. You have microsomal oxidation, which occurs in the endoplasmic reticulum. You have nitric oxide synthase right here. This is an immune enzyme, so it's involved in your immune system. You don't need to memorize that. You have NADPH oxidase, also an immune enzyme, immune system. What do we call it? We have transition metals, as we mentioned. We have iron, copper. We have myeloperoxidase, again, another immune enzyme, immune. And we have the electron transport chain, obviously, through aerobic respiration. These are all sources of reactive oxygen species and reactive nitrogenous species. Remember, these are mostly bad for your bodies. They're not totally bad. We'll discuss why they're useful when in the right context. But for the most part, you can think of them as bad. So, again, we mentioned their production. Now, this is where you know what to focus on. So, neutrophils, by the way, are cells of immunity. They're white blood cells. They're one of the types of white blood cells. So they're involved in immunity. They produce these free radicals to kill bacteria. So, well, free radicals aren't bad. But the thing is, these free radicals are contained in a space known as the phagolysosome. Now, you don't need to know the specifics of this. All you need to know, it's just a special lysosome. I think you guys know what a lysosome is. It's just the organelle inside the cell that breaks down specific organ, like different proteins and organelles inside the body. All you need to know is that this reactive oxygen species are produced inside this contained space of a phagolysosome. The reason it's produced in there is because the immune cell eats the bacteria. It eats bacteria. and it shoves it in that lysosome. Once it shoves it inside the lysosome, it dumps a bunch of reactive oxygen species and kills it. That's how it works. Now, what do we call it? Now, let's leave immunity for a second. Now, it says over here, reactive oxygen species occur at a slower rate when there's oxygen. So when you have enough oxygen around, so your cells can work just fine, everything is working just fine, there's low levels of reactive oxygen species. Now, the problem happens is that obviously it still generates free radicals, by the way. Like under normal conditions, free radicals still form by the electron transport chain, like the respiration and all of that. It still forms, but your protective enzymes can deal with it at the time, like catalase. They can like deal with the problem. They can quickly reconvert the free radicals that were mentioned earlier over here. Remember this stuff over here, this whole antioxidant defense that we mentioned over here. They can quickly deal with the free radicals. The problem happens when there's a reperfusion injury. The reason it's called a reperfusion injury, I'll discuss it in just a second, the next slide. So all you need to know is that a blood vessel gets blocked. When it gets blocked, no blood reaches the tissue. When there's no blood reaching the tissue, all that means is that there's no oxygen around. As we mentioned, oxygen slows down free radicals. When there's no oxygen around, that promotes the formation of free radicals, but not right away. The way the free radicals form is through a reperfusion injury. Reperfusion meaning like the blood comes back. So after the blood is blocked, for some reason it gets unblocked again and the blood comes back. When it goes back, what do we call it? It produces a lot of reactive oxygen species. Like read this line over here. So when there's no oxygen around, there'll be low levels of ATP, low levels of NADH. Remember, these are the energy currencies you form through aerobic respiration that you've been learning through MOL throughout the parallel right now, throughout the course. So in a tissue deprived of oxygen, in the case of, for example, a heart attack, when oxygen is suddenly reintroduced, so oxygen again happens to enter again, suddenly the mitochondria is hit with a whole lot of oxygen, and it activates the electron transport chain very, very much. And when it's very active, it generates a lot of reactive oxygen species in a burst. This is why this occurs. I'll clarify it here on the diagram. So let's imagine a blood vessel right here. This gets blocked for whatever reason. Say there's a piece of popcorn in here or something. So when it gets blocked, whatever is beyond this point gets low oxygen. So all cellular mechanisms start to decrease. Everything starts to fall. However, for whatever reason, say we apply something that unblocks the artery, the blood comes back. So the blood is flowing again. This reintroduces oxygen. Oxygen starts to be reintroduced. This results in a burst of activity of cellular respiration, like glycolysis and all of that. And this results in the generation of free radicals. Yep. This is a bit confusing. Do you guys understand it? Oh, no. So it's a little bit of a misconception. It's not oxygen. Sure, oxygen does get converted into free radicals. But the thing is, normally under high conditions, so let me go back to the slide you're mentioning. Normally under normal conditions, when there's oxygen around, everything works at a normal pace. So everything's working the way it's intended to work. So your body is functioning, the cellular respiration, the mitochondria is all working at a constant speed. It's all working at a constant speed. When low oxygen occurs, no free radicals are formed yet. There's no oxygen to form free radicals, no free radicals. The problem happens when you reintroduce the oxygen suddenly. So when you unblock the artery, for example, you reintroduce oxygen very quickly. And this causes the electron transport chain to increase its activity very quickly, like more than when it was working under normal conditions. And this generates a lot of free radicals. This is why this occurs. Do you want me to repeat again? Or is it clear? So remember, it's normal conditions. Everything is normal usually. In normal conditions, your body can deal with it just fine. That's why it's called normal. Remember, normal means your body deals with these free radicals. The problem happens is when there's a problem in the body. For example, a blocked blood vessel. When you reintroduce oxygen very quickly, it causes the electron transport chain to fire very quickly. And this electron transport chain will generate free radicals because of its burst in activity. This is how the electron transport chain generates free radicals, if you're curious. So I guess I'll move on to the next point. If anyone wants me to repeat that, just type in the chat or is confused about anything. All right, so generation of free radicals. Again, how does it generate? So we discussed a few mechanisms. Let's discuss other mechanisms. So remember, 1 to 4% of oxygen in the body is converted into free radicals, but your body can deal with it normally. So protective enzymes can usually deal with this. Deals with this. Now, there are other ways that the free radicals form inside the body. So number one is through cellular metabolism, just by existing. You, just by existing, form free radicals. This could be through the electron transport chain, which we just discussed. This could be through enzymes known as xanthine oxidase or aldehyde oxidase. Just remember these enzymes. You don't need to know how it forms these free radicals, but they do form free radicals. Just remember these enzymes. They have oxidase in them, so that makes them very easy to remember. Just remember oxidase. And finally, macrophages. Macrophages are immune cells, and immune cells use free radicals to kill bacteria. So they're antibacterial. So these free radicals are good. So it produces a nitric oxide free radical. Remember that. This is what it produces. Anyways, again, this is the electron transport chain. We already discussed it. Right here, it generates free radicals just by working. There's nothing new over here. Generation of free radicals through the electron transport chain. This is where most free radicals are generated. Electrons passing to molecular oxygen directly. Okay, cool. So this is usually neutralized. So these free radicals, as we mentioned, are neutralized by superoxide dismutase. Remember this diagram over here? Where was it? This guy over here? Remember this is the exact same thing. It's just repeating it in words again. All right. Another enzyme, another oxidase that generates free radicals is known as NADPH oxidase. Now, from its name, you can know that it uses NADPH. NADPH oxidase. This occurs in a phagosome or a lysosome, to make it easy for you guys. It's just a modified lysosome inside immune cells. This is in immune cells. Remember, this occurs only in immune cells. Immune cells. So what happens is NADPH oxidase converts normal oxygen into the free radical. Now, this free radical, you don't need to know this process from here. All you need to know, this generates a free radical, but I'll explain the process anyways, just if you're curious. So this free radical, as we mentioned, gets converted to hydrogen peroxide through superoxide dismutase. Now, what happens here is through an enzyme known as myeloperoxidase, or on its own, if left on its own, it generates the hydroxyl free radical, or this free radical right here. This eventually results in the killing of bacteria. This is all this does. So this enzyme generates free radicals to kill bacteria. That's literally all you need to remember here. Free radicals produced by neutrophils, released extracellularly, fast, high output, inducible, and bactericidal. So free radicals, the gist of the slide, free radical by immune cell, by immune, to kill bacteria. That's it. That's literally the whole slide. That's all you need to remember here. And remember the name of the enzyme, obviously, NADPH oxidase. All right. Next. Again, this is pretty much the same thing, same as before. HMP shunt, by the way, is the pentose phosphate pathway. This is how NADPH is generated. If you remember, I think you guys covered a PAL on this, and you took it. I took this lecture on pentose phosphate pathway. NADPH is used in NADPH oxidase to form the free radical, which kills bacteria. Again, this is just a repeat. So it kills bacteria, kills viruses. This is how your immunity works. Now, we've been discussing how cells make free radicals. Now, the environment can also make free radicals. How does it make free radicals? Well, it makes free radicals through drug metabolism. Oh, sorry, not the environment. I meant the outside. It doesn't have to do anything with the cells. It's not necessarily from the environment. Not to do with cells. So it could be through drugs, like medication. It could be through UV light damage or X-rays, or it could be through cigarettes and alcohol. This is why these things are bad for you, by the way. The reason we say don't smoke, don't stay in the sun for too long, don't drink alcohol, and why medications have side effects The reason medications have side effects is because of the generation of free radicals, because they do generate free radicals. Cool. Anyways, so here are the sources of exogenous free radicals, exogenous meaning from the outside. So it could be from radiation, UV light, X-rays, gamma rays, just know this. Chemicals, for example, ozone singlet. Chemicals that perform peroxide. Again, this is all examples. Just you don't need to memorize this per se, but just remember that you can form them from the outside. The most important thing to remember is that these are harmful to you from the outside. Anyways, so again, this is the same thing: smoking, diet, medications, water pollutants, fast food, stress, alcohol, pesticides, toxins, fruits, vegetables, all of these, what do we call it? Cause formation of free radicals. By the way, formation of free radicals is also known as oxidative stress. Formation of free radicals, or reactive oxygen species, is also equal to oxidative stress. Oxidative stress. That's it, really. So these things that we consider bad for us, like generally, just think about it logically. So what do you think is bad for you? So smoking, bad diet, side effects of medications, pollution, fast food, stress, all this produces free radicals. This is why they're very important. So, like, why are they harmful? So we've been discussing, what do we call it? We've been discussing why they're generated, how they're dealt with, but how do they harm you? So in proteins, what they cause is they cause oxidation of the sulfhydryl groups. Oxidation, remember, is a loss of electrons. So these lose their electrons. And this leads to modification of amino acids. And all of this results in the formation and fragmentation of protein and what do we call it? And loss of function. So proteins lose their function. Give me a second, guys. There's just a lot of yelling here. Just 1 second. Okay, I'm back. Yeah, so again, proteins get damaged by free radicals, which causes them to fragment or break down, and they cause them to aggregate. And they lose their function, obviously, and they're no longer healthy. Now, imagine if this protein is responsible for regulating cell division. If this was responsible for regulating cell division, this might be disrupted, and this might lead to cancer, for example. You don't need to remember this specific example, but this is just to give you an example. Lipids, a lot of lipids may be damaged by free radicals. This is called lipid peroxidation. What do we call it? One example is through obesity and hyperlipidemia and increased fat. When fat is increased, this leads to mitochondrial disruption, and this forms free radicals. And these free radicals kill the cells that secrete insulin. And this is why diabetes occurs in obesity. So free radicals kill the cells that form insulin, which are in the pancreas. I think you guys are taking it and covering it through GI. It's the islets of something, I forgot. But it kills these specific cells. So what does it do? What does lipid peroxidation do? It causes structural changes in membranes. So it alters their fluidity, it alters the channels, signaling proteins, ion permeability. All these are normal functions of the membrane, the cell membrane. And when it's disrupted, when you don't have a functioning membrane, you don't have a functioning cell, and the cell eventually dies. Lipid peroxidation also, like these lipids that are getting like peroxidated, which just like proteins, they're considered free radicals because this is how free radicals form. It's a cascade of reaction. And these guys form links to non-lipids, for example, proteins and DNA. And when they form links to these molecules, they disrupt those as well. And they kill them off. They destroy them. Direct toxicity. So they cause direct toxicity. They kill the cell directly. Don't just memorize this. Don't specifically any of this stuff. It disrupts membrane signaling. We already discussed this. And it causes DNA damage. So DNA damage obviously causes mutations, and mutations can lead to cancer as well. There's a question in the chat. So free radicals cause lipid peroxidation, which creates even more free radicals. That is correct. Yep. All right. Yep, you're welcome. All right, so harmful effects of free radicals. again, this is just okay, I got confused for a second. Sorry, guys. So this is in carbohydrates. What happens is glycation, which increases susceptibility of proteins to be attacked by free radicals. All this does, basically, all you need to know, when they get glycated, they get attacked, basically. Nucleic acids also get affected by free radicals. We said lipid peroxidation affects it as well, causes DNA damage, but like free radicals can also directly attack the DNA as well, which causes it to break, and obviously that's bad. It causes mutations, and these mutations, what do we call it, result in cell death. All right. Again, there are specific diseases that occur when free radicals are formed. These include diabetes, cataracts, male infertility, aging, others. You don't need to know specifically how any of this happens. You don't need to know how literally any of this happens. It doesn't matter. But all you need to remember, diseases occur because of free radicals. For example, diabetes mellitus, cataracts, which are problems in the eyes. Their eyes. Male infertility, aging itself has to do with free radicals. And there are other diseases like Parkinson's, Alzheimer's, cirrhosis, multiple sclerosis, muscular dystrophy. I need to remember free radicals cause diseases. That's all you need to know. So again, these free radicals cause diseases: chronic heart disease, cardiac fibrosis, skin aging, chronic kidney disease, etc. And they cause it in literally every organ in the body, every system. All right, so one last correlation over here. I don't think this is too important in my opinion. But all you need to know is that in some patients, some people have a missing NADPH oxidase. Now, this enzyme, if you remember correctly, it's the immune enzyme right here. It's this guy. So your immune cells no longer work correctly. Your immune cells just don't work anymore. PMNs, by the way, are neutrophils. Neutrophils. They're neutrophils. And they're not working correctly. So all they do is, because these free radicals can't be formed by the neutrophils, they can't kill bacteria. You don't need to know these specific bacteria: Staphylococcus aureus, Klebsiella, Escherichia coli, Candida. You don't need to know this stuff. This you'll take in POD next year. But all you need to know is that the neutrophils can't kill off the cells. And when it can't kill off the cells, they start accumulating. They can't kill off the bacteria. And if they can't kill the bacteria, they can't get rid of them. And what happens is it causes something known as a granuloma. Granuloma isn't a cancer, but what happens is the immune system walls off the bacteria. So it forms a wall around the bacteria because it can't kill them. You don't need to know this stuff. Just remember literally just memorize this definition, because you'll take this next year and it'll be more clear then. You might not understand this right now at the moment. So there's a stain over here known as nitro-blue tetrazolium. Nitro-blue tetrazolium, when you stain a cell that has NADPH oxidase, it will stain. That's because these cells don't have NADPH oxidase. They are negative for this stain. So yeah, that's it for chronic granulomatous diseases. If anyone has a question, you can leave it in the chat. I'll just move on here. Again, medications can be metabolized to free radicals. We already discussed this. For example, paracetamol or Panadol, Tylenol, they can cause problems because if you take too much Panadol, you'll die, you'll overdose. The reason you overdose is because of oxidative stress, because they damage the kidney and the liver, and this is why side effects occur. And these get aggravated by alcohol, cancer therapy, steroids, antiretrovirals, whatever. These are all side effects of these medications. You don't need to remember this stuff right here. But just remember, medication leads to free radical, which leads to side effects. Side effect. That's it. That's all you need to remember here. You don't need to remember the specific details. Just remember, too much drug causes free radical, causes body damage. This is just a balancing slide. You don't need to know this. Like, this is just a summary, really. Other than that, We already discussed the defense against excessive free radicals, or sorry, reactive oxygen species. Remember these two enzymes, superoxide dismutase and catalase. Remember these two from the beginning, way over here. Let me find them real quick. Yeah, right here. Remember this, superoxide dismutase and catalase? We already discussed this. This is the defense mechanism inside your body. And this is how it clears off these free radicals. Right here. So anti-inflammatory agents, oh, sorry, my bad. Yeah, I was here. Superoxide dismutase and catalase. These are present inside your body already. They're in body. In RBCs, superoxide can be produced, but usually it's cleared by, what do we call it? These two enzymes. So again, all you need to know here, you have a bunch of enzymes that neutralize these free radicals. These are known as superoxide dismutase, catalase, glutathione peroxidase, the one we discussed earlier. And there's a bunch of other things that are considered free, antioxidants inside your body. Just remember them. You don't need to know how they work, but vitamin E and vitamin C are, what do we call it, are one of the some of the vitamins that are involved in what do we call it, involved in antioxidant defense. So vitamin E is in membranes, vitamin C is in the cytoplasm. You just need to remember this, nothing specific about it. In RBCs, again, we're talking about red blood cells. Red blood cells. This is all in red blood cells happening. But by the way, these defense mechanisms are not only present in red blood cells, they're present everywhere else. But this specific example is focusing on RBCs, or red blood cells. If these enzymes are not present, any of these enzymes are not present inside the cell, or any of their precursors, they lead to something known as hemolysis, which means breakdown of the RBC. The RBC just bursts. The reason it bursts or dies is because the free radicals overwhelm the cell and they kill the cell off. For example, if you don't have enough NADPH, because of a G6PD deficiency, remember this enzyme, G6PD. This enzyme is in the pentose phosphate pathway, or the HMP shunt, which produces NADPH. And remember, NADPH, where do you need it? You need NADPH in this reaction right here. You need it right here. If you don't have NADPH, you have accumulation of free radicals right here. So this is why G6PD deficiency is bad. Let me find it. All right. So that's it for that. Do you guys hear me? Do you guys still hear me? Yeah, okay. Okay, cool. My thing cut out, that's why. So they sacrifice themselves in order for the other cells to be, they sacrifice themselves in order for other molecules to not be damaged. So they're considered anti-inflammatory agents. They're inhibitors of nitric oxide synthase. They could be metal chelators, transferrin, lactoferrin, metallothionein, NADPH oxidase inhibitors, and xanthine oxidase inhibitors. All you need to know here, basically all this is, remember the enzymes we said that produce free radicals? Remember those enzymes? If you give inhibitors to them, they stop making free radicals. This is all this means. And for metal chelators, a chelator is something that binds the metal. If you bind the metal, it no longer is considered to be a free radical. So these could be through these examples right here. Just remember one of them. I would recommend remembering this guy. Transferrin. Transferrin is very common. Finally, this is just a summary of everything. This is reactive oxygen species in the RBC. Again, through the glucose, pentose, phosphate pathway, remember this guy, G6PD, remember this enzyme that produces NADPH. This can be used to reduce glutathione through glutathione reductase. Reduced glutathione can sacrifice itself to neutralize the free radical. You see this free radical right here, hydrogen peroxide. This free radical can be converted into water after glutathione sacrifices itself. If this free radical is not cleared in RBCs, remember this is in RBCs, but it could happen in other cells, but we're focusing on RBCs. If it's not cleared for whatever reason, say there's a deficiency of this right here, this enzyme is not present, so there's no more NADPH. You can't clear this anymore, and this accumulates inside the cell. And this causes the hemoglobin, which is the thing that carries oxygen inside the cell, to be denatured, which means misfold. It's the protein. It becomes misfolded and forms something known as Heinz bodies right here. You'll cover this in heme next semester again, so don't focus on it too much. And this causes the death of the cell, basically. So yeah, that's about all. Are you guys confused about anything? It's a very short lecture, very easy. If there's any confusion, just let me know, guys. I can repeat any points because we're done, honestly. Any confusion, any problems, any misconception that you want me to deal with, anything? Any questions? All clear? All right. I'll wait like 1 more minute. All right. Thank you, guys. Yeah, that's about all. I guess we're done. If you have any questions, I left my email at the beginning of the presentation. You can just what do we call it? You can just email me there, and don't worry about it. I wasn't watching the match anyways. All right, so yeah, that's about all. You guys can leave. Whoever's recording can stop the recording. We're done. Thank you, guys.